I think you have selective hearing.
I have selective hearing. I do have selective hearing. Just like any parent has selective hearing, I have selective hearing too. Um, okay, okie dokie. So don't worry, I have no plans for a final. That's too much work. Um, okay, so to get started, um, there is a graphic organizer on Canvas. I will link here if you want to fill out. Okay, so basically, so why is the first hill of a roller coaster the tallest? Why do you think the first hill of a roller coaster is the tallest? And do you think it's possible for the second hill or any subsequent successive hill to be taller than the first? Why or why not? Why is the first hill of a roller coaster tallest? Is it possible for any second hill or any other successive hill to be taller than the first? Why or why not? Why is the first hill the tallest? Is it possible to have a second hill that is taller than the first? Have I told you guys that I can't really do roller coasters anymore? They just make me super nauseous. Like I can't even do swings anymore in a park. I once like went on a swing and I started going back and forth and I felt like I was gonna puke. So this is what happens when you age. You're supposed to say, Mr. Who, you're not old. You're plenty young. You can't go on boats? Okay, that's like logical though. And do I have inner ear problems? I don't think so. But yeah, I can't go roller coasters anymore. I went to Six Flags for my friend's birthday, and I felt like I was gonna puke the whole day after. So like it took me like 2 days to recover from it. That was rough. No, so I mean the day of I felt horrible, and the day after I felt horrible, and then it wasn't until the day after the day after that I felt okay. Yeah. Uh-huh. It, oh, for me, my biggest fear is like losing a shoe or something on a ride. Like that's my biggest fear. Take a Dramamine and stop being a coward. Wow, that's very supportive. I'm really glad that you feel I'm a young buck. Thank you for thinking that I'm a young buck. I am old. I'm lame. I'm a boomer apparently. That's all pretty messed up. I only recently got to go on all roller coasters because I'm super short. Now all the parks are closed. Rip. Yeah, I think I started going to like all the rides at Great America when I was like in middle school. back in the day when they had Invertigo, I don't know if any of you were alive when they had Invertigo. I think they like sold it and shipped it off. But Invertigo was a super sick roller coaster. That was pretty wild. I think they sold it and shipped it off another place. Invertigo was removed in 2011. Yeah, I don't think you guys were born in. I don't think you guys were alive in 2011. How old are you guys? Like 5, 6 years old? Yeah. So how old are you guys? Like 7, 8 years old? 9? Yeah. Yeah. So you're like what, 7 or 8 years old? Yeah, that makes sense. Uh huh. Cool. It's really cool. It's really interesting. Yeah, I was born in the 90s because I'm a 90s kid. Only 90s kids would get this reference. This is a tough crowd today. Tough crowd. I think I'm really funny, but okay, clearly I'm not. Okay, so we have a lot of good responses. Okay, so the first hill is the tallest, so it can build momentum for the rest of the ride. The second hill cannot be taller unless there's some sort of mechanism to pull the train up it. This is because it doesn't have enough speed from the first hill to go over a taller one. That is true. And I don't think I've ever been on a ride where the second hill was taller than the first. I don't think I've ever been on one where there's some sort of mechanism to do that. So the first hill is taller because it's to help build up speed needed to complete the rest of the course. And I guess there could be ones taller, but they would need some sort of pulley to go up the hill. Yes, exactly. Some energy is lost to friction, I believe. So when traveling down a roller coaster, so a roller coaster at the same section towards the end of the ride with the same elevation as a section at the beginning of the ride is going to have a lesser velocity. Thus, it is going to have a smaller chance of completing a higher hill, the more friction that is lost as the ride progresses. That is an excellent response. Good ideas there. I think the first hill of a roller coaster is the tallest because it is used to generate a high velocity going down and over subsequent hills. But given that the first hill usually relies on applied force to bring the car to the top, I would say that it is possible to have a subsequent hill that is taller than the first. Because it gives the most speed after going down, meaning it will be able to have the most ability to make it through the rest of the ride. Not unless there's a cable pulling it up, because the velocity won't be able to make it up. So yeah, the general trend is there. It theoretically could be tall. The second hill could be taller than the first, but you would need some sort of thing to bring it up. And we will talk about that quite a bit today. Hills take a lot of energy to go up, and if done correctly, only the first hill needs a cable. The second hill could be taller, but only if it had a cable as well, since the force the car would have from going down the first hill is not enough for a hill the same size or bigger than the first. As for 2, extending the definition of a hill down to infinitesimal height is possible to have a microscopic bump somewhere at the beginning and then do a larger hill. Okay, then some people were roasting me and making me feel bad. Then it depends on the roller coaster machinery. First hill is usually the tallest, so they only have to move the roller coaster to go up a hill once. But I suppose it's long as connected to the engine. So yeah, but the thing is, roller coasters actually aren't connected to an engine. Like they're lifted up by a cable, and then afterwards it's just like a cart. So you are at the mercy of the designers. There's no actual power in it. The first hill is the tallest, so it can continue to go at high speed and go over subsequent hills. And the second hill can be taller, but the car will likely need to be pulled up, which really makes for a sad ride that ruins the fun mood. Good point. Good point. We don't want our rides to be sad. We want our rides to be exciting. So in general, I think most of you have sort of nailed it. Roller coasters are powered by gravity. So basically, the only time there's some sort of external thing going on is that when it's going up the first hill, right? It's being pulled up by a cable lift because you hear the dun 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 dun, and that's because the cable lift is pulling it upwards. So it's like, and there's no engine on the coaster itself. Like if you actually look at the roller coaster, all you see are just a bunch of like wheels on the bottom, and there's no engine or anything. So you're literally just being pulled up by the cable lift. Once you're at the top, you're being released. So the reason why you bring it up the first hill is because you're gaining a lot of gravitational potential energy. The whole idea is by bringing it up, you're gaining all this potential energy that you can use for the rest of the ride. And that's why we call it potential energy. We're essentially storing energy in the roller coaster through its elevation, through its height. And then so when it goes down, all that energy gets converted into the fun kinetic energy that we all know and love. So basically, by bringing up, we gain a lot of gravitational potential energy that we can use to convert into kinetic energy later on. So the main reason why this works is because of something called the conservation of energy. You may or may not have heard some similar things either in the past, either in chem or in biology. Okay, I don't know about biology, but in chem definitely, or conservation of mass or something like that. Basically, the idea is the total amount of energy in the system always remains the same. So this is what we call the law of conservation of energy. Energy basically cannot be created nor destroyed. So if I have 100 joules of energy to start off with, at every point in the right, we will always have 100 joules, no less or no more. So if we wanted to change the total amount of energy in the system, we would have to apply what is called work, which means external energy to the system. Basically, any system that is sort of left alone to do its thing will have, I mean, every system in general, every system, period, will always conserve energy. Basically, the amount of energy in the system will always remain the same. You can't create or destroy energy. If you have 100 joules in the beginning, you have to have 100 joules at every point in the bride. If you want to change the total amount of energy in the system, you would have to apply work, which means you are applying external energy to the system in order to do so. But energy is always conserved. If you think about if you apply work to that, actually, I'll talk about that later. Basically, yeah, you have energy is always conserved. You have 100 joules to start off with, you always have 100 joules. You want to change that, you have to apply work to the system. You have to do work. So this is really important because this is the main principle behind roller coasters work. The idea is because energy is always conserved, what this means is that the total energy in the system has to remain the same. However, this doesn't mean that the individual energies have to remain constant. So basically, what you can think of it as there is sort of like a total energy that encompasses every single energy that the roller coaster has. So, potential gravitational potential energy, kinetic energy, thermal energy, et cetera, et cetera. There is a total amount of total energy that the roller coaster has. That total energy has to stay the same, but you can change the distributions of the individual energies. So it's like if you had like $100, you could decide you're going to put some of it in Bank of America, you're going to put some of it in Citibank, you're going to put some of it in Venmo, you're going to put some of it in your mattress. Right? There are different ways you can store the money. The total amount of money you have is the same, and that applies for energy as well. You have a sort of a total amount of energy to work with that you can distribute in different areas, and you can always change these distributions. You just can't change the total amount of money or the total amount of energy in the system. So basically, energy can change forms from one form to another as long as the total energy in the system remains the same. So the way roller coasters work is, is behind this principle where you're changing the type of energy that the roller coaster has from less fun ones to more fun ones. So the question then becomes, how do we determine the amount of total energy we have? Well, the amount of total energy we have, you could sort of you could sort of define you could define how to calculate the total energy as being it's the sum of all the individual energies. So if I take the kinetic energy and I add it to the potential energy, and then I add it to the chemical potential energy, and I add it to the thermal energy, all those energies added together is how we calculate the total energy of a system. And you could describe it as E is equal to the sum of all individual energies. The main two energies we'll be working with is kinetic and potential. So you don't really need to we're not really going to be covering exactly how to directly calculate other energies. But you can sometimes indirectly calculate other energies because you know that the total energy of a system always is conserved. So what will happen at some point is we'll be like, how do you calculate this obscure energy in the system? And then you're going to be like, I don't know how to, there's no equation for it. But the thing is, because the total energy is conserved, you can sort of sometimes deduce how much energy another energy type would have just because of the fact that the total energy has to be conserved. The main idea here is that to calculate the total energy of a system, I just need to sum up all the individual energy types to do them. So yeah, to calculate the total energy, I just take the sum of all the individual energies. The two most important ones are the kinetic and the gravitational potential energies. Those two you will definitely need to know how to calculate. Very, very, very important. The other ones we won't be covering how to directly calculate them, but there are still ways to indirectly calculate them based on the fact that total energy is conserved. So because the total energy is conserved, here are a couple of questions for you. As a roller coaster is going downhill, what kind of energy would it be gaining as it goes downhill? Gosh darn it. Wait, okay. Okay, so was it always like that or was it just now? Okay, thank you. Very helpful. Okay, that would have been really awkward if it was gone for like 10 minutes. Okay, we're cool. We're good. So if a roller coaster is going downhill, what kind of energy would it be gaining as it goes downhill? And what kind of energy would it be losing as it goes downhill? And vice versa for an uphill roller coaster, what kind of energy would a roller coaster be gaining as it goes uphill? And what kind of energy would a roller coaster be losing as it goes uphill? So what kind of energy would a roller coaster be gaining as it goes downhill? What kind of energy would a roller coaster be losing as it goes downhill? And vice versa for uphill. What kind of energy would it be gaining as it goes uphill? What kind of energy would it be losing as it goes uphill? So in general, there are two energies that we're going to be looking at here. When the roller coaster is going downhill, what does a roller coaster want to do as it goes downhill? It gets a lot faster. And the farther down it goes, the faster and faster and faster it goes. However, as it goes downhill, it also means it's losing elevation. It's getting lower and lower and lower. And so because of that, as it gets faster and faster and faster, it is gaining kinetic energy. Kinetic energy is once again the energy associated with movement. So the faster you go, the more kinetic energy you're gaining. However, as you're going downhill, you're getting lower and lower and lower. So that means you're going to be losing gravitational potential energy, because gravitational potential energy is dependent on your elevation. So the lower you are, the less gravitational potential energy you have. Vice versa, going uphill, what kind of energy would it be gaining as it goes uphill? This is sort of the opposite, right? As you're getting uphill, you're going to be getting taller, your elevation is going to increase. So you're going to gain gravitational potential energy. However, as you go uphill, you also slow down. So that means you are going to be losing kinetic energy. As you go down, you gain kinetic energy and lose gravitational potential energy. As you go up, you gain gravitational potential energy, but at the cost of kinetic energy. So basically, the idea here is that in both scenarios, the total amount of energy is the same. So if one energy type is increasing, the other one has to decrease. So you can't change the amount of total energy. You can only. Also on roller coasters, there's always that little moment at the top when you pause, but that I thought that was just to build tension in the passengers. That's sort of because the cable lift like sort of stops pulling you up. So it's sort of like it pulls you up just to the point where you basically stop moving, and then the weight of the roller coaster starts making you fall down. So you can think of it. I mean, it is there to build tension, but it's also like the cable lift stops pulling you up at a certain point. Yeah, it basically like waits for your roller coaster to start falling, and then it just So gravitational. So sort of with a roller coaster, that part is sort of the pseudo drop is so that the chain on the lift doesn't get strained by an initial drop. Without it, the velocity of the front cars going down will pull the back cars still on the chain down, and that would damage the ride. That's actually really interesting. Yeah. So yeah, that's actually really interesting. So yeah, so the pseudo drop is so that the chain on the lift doesn't get strained by an initial drop. Without it, the velocity on the front cars going down would pull the back cars, which are still on the chain, down, and that would damage the ride. Yes, that actually makes a lot of sense. Yeah, thank you for pointing that out. So I am definitely not an expert on roller coasters. I have a friend who's much better at this, but I can't convince him to teach. Okay, so I think with gravitational and potential energy and kinetic energy, that's a little bit more straightforward. So here's a different scenario. How would a car braking demonstrate the law of conservation of energy? How would this demonstrate the law of conservation of energy? So how would a car braking demonstrate that energy is still being conserved? Because it's not really an intuitive example. Right, the car is initially moving, so it has kinetic energy, and then when it stopped, it doesn't have any more kinetic energy, so the energy had to go somewhere. But somehow the energy still has to be conserved. So how would it be possible for a car that has kinetic energy to suddenly have no more kinetic energy? How is that possible? So this is where we need to think about what is happening when your car is braking. So when your car is braking, basically it's sort of like if you've ever seen a bike brake, you have these little pads on it that sort of come into contact with a tire and then or the rim of the wheel, and then that starts rubbing. Basically, it's sort of like you're basically like grabbing on the tire and you're just sort of letting it like sort of slow down. So during that process, it's that contact is generating a lot and a lot and a lot of heat. Um, so if you ever brake really quickly on a bike, you'll feel that your tires and your brake pads are getting warm. And same with your car too. The faster and faster the harder and harder you press the brakes, the more and more the tires and the brake pads will warm up. So basically, what's happening is that you are using friction to essentially convert the car's kinetic energy into heat. You're basically turning all the car's movement to you're basically using all of your car's movement to convert kinetic energy into heat energy, also known as thermal energy. Um, how much would you have to brake to cook an egg on your car tire? So I mean, you could definitely calculate that. I saw this video where this person cooked a chicken by slapping the chicken like millions and millions of times. So literally, they built a machine. They took a raw chicken and they built this like mechanical slapping arm, and then they go brr, 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 and they basically use the conservation energy to cook the chicken. They actually did succeed. So the first time they failed, they built a new rig that actually succeeded in cooking the chicken. It's really interesting. It's really, really, really interesting. And that's like perfect example. We should watch the video actually. It's really interesting. Maybe I'll pull it up towards the end of the class. But basically, you have the mechanical arm is generating tons and tons and tons of kinetic energy, and then so all that kinetic energy when you're slapping the chicken, it's just being converted into thermal energy into the chicken. So if you do it enough times, it will heat up the chicken, and that's literally how conservation of energy works. It's pretty wild. I think they did it with like a. I think they did it with like a really. I think they did it with a chicken. Yeah, they did it with a chicken. They also did it with like a steak. It was really interesting. It's really interesting. Really interesting video. Definitely worth checking out. So you can usually when we work with conservation energy, we usually like to calculate the two energies that we care about the most. So in terms of calculating kinetic energy, the equation is pretty simple. The kinetic energy equation is just 1/2 times mass times velocity squared, 1/2 mv squared. You will 100% use this equation a lot. And this is actually something that I would almost encourage you to know by heart. I don't want to say memorize because that's like, but it's something that you should know very well. Just like force is equal to mass times acceleration, kinetic energy equals 1/2 mv squared is something that you should know by heart. Very, very, very important equation. I think I think you definitely use this in chem too, but you definitely use this a lot. So the kinetic energy is 1/2 mv squared, 1/2 times the mass times the velocity squared. Something you should definitely know, 100% know. So I think you'll eventually do it enough where it'll eventually just like get engraved into your brain. So there's nothing crazy about this. Kinetic energy is 1/2 mv squared. The next equation that we will want to know is how to calculate the gravitational potential energy. The gravitational potential you can calculate by m times g times h. We usually use the variable u. There's a lot of variables that we actually might use for gravitational potential. U is common. The problem with G, capital case G, is that there is a variable, a constant called gravitation, capital G, and that is the problem is that we're sort of at a point where there's too many variables and stuff, so we have to use these really weird ones. So U is for gravitational energy. I mean, sometimes you might write it as just GPE. I think I've seen the equation looks like a noise people make in frustration. I think I've also seen people use V for this too. I can't remember. And I've seen, and I think when I was in college, I think we used V for gravitational potential energy, and I think we used T for kinetic energy. So there's a lot of really weird variables for this. Now the general formula itself is mgh, mass, times g, little case g. Little case g is the gravitational acceleration, which is 9.8 meters per second squared. And then h is the height of the object. So m times g times h. There's also another form where it's like gmm over r squared. That one is like a more, I guess like a big picture. Like that is like the more. This is like a simplified version of that essentially. It's like that's like the rectangle, and this is like the square. So we usually use this. The potential gravitational potential energy is the mass times gravity times the gravitational acceleration times height. You will also definitely need to know this one for sure. For show. So m times g times h. The thing about the height of the object is that this is kind of interesting. So the gravitational potential energy is relative. So basically, we can say that any point, we can set any point in the world as being this point has 0 gravitational potential energy, and then we compare the gravitational potential energy of other objects relative to that point. So usually what we say is the ground has 0 gravitational potential energy. So then we use, and then we just say, okay, this thing is 10 meters above ground. So we're just going to calculate the gravitational potential energy, assuming that the ground is 0, and then this thing is 10 meters. However, if let's say we were working with a table, and so what I was saying is I'm lifting this 5 feet above 5 meters above a table. If we're using a table, it probably doesn't make a whole lot of sense to use the ground as a reference point because we're lifting something above a table. So then it actually makes more sense to actually use the table as a reference point. So then what we would say is that the table has 0 gravitational potential energy, and then we would calculate the potential energy of the object relative to that. So basically the idea is we can set any point we want as being 0, and then we can measure the gravitational potential energy relative to that point. Does it still work if let's say I was lifting something 5 meters above the table? Does it still work if I use the ground as a reference point? Yes, it still does work. But what ends up happening is that it's still very viable. It's still very viable. You just have to instead, but what that means is you have to take into consideration both the elevation of the object and the elevation of the table. So basically what you're saying is, okay, the initial object is 10 meters above the ground, but the table is 5 meters above the ground. Whereas if you set the table as being 0, you only have to consider that the object itself has 5 meters worth of elevation. So it's actually simpler. You can do a lot more if you're good with setting your zeros for your gravitational potential energy. That would be a very tall table. 5 meters is what, 15 feet tall? Yeah, that's actually correct. Yeah, so I don't have a clever response to that. I'm sorry. I apologize. So here are a few practice questions. So basically, the first question what I want you to do is if a 1 kilogram mass is being held at 10 meters above a table, you just use cheers. If a 1 kilogram mass is being held at 10 meters above a table, how much gravitational potential energy does it have? And then how much total energy is going to be present in the system? So that is the first question. If a 1 kilogram mass is being held at 10 meters above a table, how much gravitational potential energy does it have? How much total energy is present in the system? So once you do that, then try to figure out how much, actually, no, before I let you do the second one, I think we'll go over the first one. So if a 1 kilogram mass is being held at 10 meters above the table, how much gravitational potential energy does it have? This is pretty straightforward. We're just going to use the gravitational potential energy equation. So U is going to equal m times g times h. The mass is 10, g is 9.8. The height is, the mass is 1. The height is 10. So 1 times 9.8 times 10 is just 98. So this has 98 joules. Joules is the unit we use for energy. So this thing has 98 joules of gravitational potential energy. How much total energy do we have in the system? In this case, we are holding the mass above the table. So the mass itself is not moving. So it would have no kinetic energy. So the total energy would also be 98 joules of kinetic energy, potential energy, sorry. So now that we know the potential energy and the total energy when it's being lifted above a table, when it hits the table, how much kinetic energy will it have, and how fast will it be moving? When the mass hits the table, how much kinetic energy will it have? How fast will it be moving? And how much total energy is present in the system during this scenario? So to do this, it would be first helpful for us to figure out how much total energy we should start off with. That always gives us a good grounding point to work with. So in question 1, what we found is that there was 98 joules of total energy. So that means going into question 2, our total energy should still be 98. So the amount of our total energy will equal our potential energy plus our kinetic energy. Plus et ceteras, but we're not going to worry about the et ceteras because we're not considering them in these problems. So we found out that in our previous problem that our total energy was 98. So 98 should equal our potential energy plus our kinetic energy. So for this problem, the mass has hit the table. So basically what we're doing is we set the table as we're basically comparing the elevation of the mass with respect to the table. So we're basically saying that the table itself has 0 gravitational potential energy. We're saying that the table has 0 elevation. So when the mass hits the table, it no longer has any gravitational potential energy. So the U becomes 0. So that means that all of the potential energy has been converted into kinetic energy. So our kinetic energy should equal 98. So then 98 will just equal our kinetic energy. Our kinetic energy formula is 1/2 mv squared. So what this means is that what that means is that our velocity should equal 14 meters per second if we do the math out. So basically what we realize is that the total energy has to be the same. We then realize that the mass has hit the table, which means that its elevation is now 0, which means that all the total energy has now been converted into kinetic energy. So then we just use the kinetic energy formula and we figure out the velocity of the object. It's 14 meters per second. Okay, so now we're into the last problem. When the mass is halfway down, how much gravitational potential energy does it have? How much kinetic energy does it have? And how much total energy will be present in the system? So now we're going to do the last one. How much potential energy, how much kinetic energy, and how much total energy would it have at this point? Okay, so how much, first off, I think we can first start off with identifying how much total energy we should have in the system. Because once again, we know that our total energy should be conserved. So once again, our total energy, we know that we start off with 98. We know that 98 should equal our potential energy plus our kinetic energy. So in terms of figuring out how much kinetic energy and how much gravitational potential energy we have, I think it probably makes more sense to first figure out the gravitational potential energy, since we know that the mass is halfway down. The fact that the mass is halfway down gives us a big clue in terms of how to figure this out. That means our height should now be 5 instead of 10. So to figure out our gravitational potential energy, this is going to equal m times g times h. Our m is still 1, our g is 9.8, but our height is now 5. So this should equal 49 joules. So notice here that when our height drops by half, our gravitational potential energy also dropped by half. So what this means is that we now know the gravitational potential energy. We can now use this to figure out our kinetic energy. So if our gravitational potential energy is 49, this means that our kinetic energy is 98 minus 49. 98 minus 49 is 49. So that means our kinetic energy is also 49 joules. So that's just a pretty standard question where you basically figure out how much total energy you have, and then you use that to figure out how the gravitational and kinetic energy are going to be arranged depending on the situation itself. Okay, so the next thing we are going to look at is, so these problems are sort of when we assume that the system is isolated, I guess. There's no external influence. Most of the time, we are going to be assuming that the system is isolated and has no external influence. Occasionally, what will happen is that the system might have an external influence. And this is what we call work. So if we want to change the total energy of the system, because the total energy is usually conserved, we can do what we call do work to the system. When we do work to the system, we are applying external energy to the system to change the total energy of the system. Now, basically, this is where we get into like, this is basically when we look at if the system itself has 100 joules of energy and we do 50 joules of work to the system, now we have 150 joules of energy total in the system. So now we change the total energy we have in our system by doing work to it. Now that amount of work we did, that external energy has to come from somewhere else. So that energy was not created out of thin dust. That actually came from somewhere else. So we took a look at the big picture, like the system of the system. Yes, doing work is basically just making a bigger system, exactly. So previously what we do is you look at a smaller system. When you do work to it, you're basically looking at a bigger system, and you're looking at this energy came from here, and now we are applying it to our original smaller system. So in a big picture sense, we didn't really create or destroy energy. We just shifted around energy from this location to this location. But the location we were looking at, the smaller location, that total energy did change because we shifted energy towards it. So that's what we call doing work. That's what we call doing work to a system. What I want you to think about is that work is only done by external energies. When a system is left to do its thing and be natural and do its own thing, there is no work being done. When a system, you have to be physically doing something external to the system to do work to it. If you just let it do its thing, there's no work going to be done. No work done when you just let it do its thing. So how do we calculate the work we do in a system? The work we do in a system is just the change in the total energy of the system. So if the system originally had 100 joules of total energy, and then after later on, the system now has 150 joules of total energy, we did a total of 50 joules of work to it. We changed the total energy of the system by 50 joules. You can calculate the amount of work you do also by force times distance. I'm not sure how much we'll use it in this class because of how much time we have left, but this is another way of calculating the work you do is by figuring out how much force you apply over how much distance. If you know calculus, the work you do is actually the integral of force times distance, essentially. So yeah, the work you calculate by two ways. You can calculate it by the change in the total energy, or you can calculate by the amount of force you apply times the distance. So if a roller coaster is going down from, so a 1,000-kilogram roller coaster is going down from a 100-meter tall hill. So how much work is being done in this system? Then I want you to think about the opposite case. How much work do you have to do to bring a 1,000-kilogram roller coaster to the top of a 100-meter tall hill? So how much work is being done when it goes down from a 100-meter tall hill? How much work is done when you bring it up to the top of a 100-meter tall hill? So in the left example, the roller coaster is falling down naturally. We are not doing anything ourselves. We're just letting it fall down naturally. So because of this, the amount of work that is being done in the left scenario is actually 0. We actually don't do any work in the left scenario because we just let the roller coaster fall itself. This one can actually be kind of tricky. A lot of people, a lot of times, they'll try to calculate the amount of potential energy here, and then they'll say that that was the amount of work being done. But the thing is, we are not actually doing anything to the coaster. It is just falling naturally. So the amount of work done is just 0. However, in the opposite case, the roller coaster does not naturally want to go up the hill. So I guess one thing that I should probably have made more clear is that the roller coaster was initially stationary. If the roller coaster was moving, let's say the roller coaster was moving fairly fast, it would actually be possible for the roller coaster to go to the top of the hill without you having to do any work if the roller coaster was moving fast enough. But I probably should have made it more clear that it was initially stationary. But if it's initially stationary, it won't want to go up to the top of the hill. So then you have to figure out how much work you have to do. So the roller coaster at the top of the hill would have MGH, so 1000 times 9.8 times 100. So this is how much potential energy the roller coaster would have at the top of the hill. At the bottom of the hill, the roller coaster has 0. So the amount of work you have to do will be the difference of the two. So in this case, it will be 980,000 joules of work, basically. At the top of the hill, it has this much potential energy. At the bottom, it has 0. So you have to do 980,000 joules of work in order to make it move to the top of the hill. Okay, so that's pretty much it for all you need to know in terms of work. It's basically that it's change of potential energy. So the last thing we're going to do is just try to re-answer the warm-up question. Would it be possible for a roller coaster to go up a second hill taller than the first? Would this be possible? Once you do that, we only have 10 minutes left, so you can finish up any parts of the Roller Coaster Tycoon where you haven't finished yet. So you can do that the rest of the time when you finish this part. It's 9:49, by the way. You still have like 6 minutes. Where's Allie? You know where Allie is today? Wait, what AP tests do you have left?
What you say?
Okay, we're out of time now, so I'll see you guys on Thursday.
See ya.
Bye, Mr. Yu.
Thank
Thank you.
you.
Thank you. Have a nice